Alright, so we're going to broaden our kind of definition of conics and look more at the geometric interpretation. So we have our ellipse, we have our parabola, and we have a hyperbola, and we can talk about how these are related in terms of their foci. And so we have properties if we had like light rays within these pieces. So if I have a light ray here, it'll bounce off the side and go through the other focal point. And then in a parabola, we have the ability to have reflected rays travel in, and then they'll come back out parallel to the line that to the axis of symmetry. Also go through the focal point, and then for a hyperbola, they diverge backwards through the other focal point. And those are used in certain applications. As you'll see as we kind of look at a couple here in a second, we have this ability to use those properties in our kind of real-world engineering components. So you have something like a whispering chamber, which is elliptical, and if you stand at a focal point where these two people are, those sound waves that bounce off, they go into the other person's ear. You have parabolic microphones, which again are able to gather sound waves and then focus them through a microphone that's located at the focal point of the kind of the bowl shaped. That's another example of a parabolic microphone. And then you also have solar energy within these panels. They have a tube of oil that runs through, or some heating element that runs through the focal point, and the light rays come in and they all concentrate on there, giving a lot of high energy at one point. Just to give you a sense of size, right, that we have people here in the middle that are kind of walking down. So these are very large pieces of equipment to use to harness the energy. All right, and so we can start to define a term for us, which is this eccentricity, this eccentricity ratio, which is the distance between a point on a conic section and the focus, and the distance between the same point and the directrix. So we have directrices for ellipses. We have one here and one here. For a parabola, one here and one here. And then for a hyperbola, they have two as well that are on this concave side of our shape. And so we define some ratio for our eccentricity as d2 over d1, where this is d2 and that's d1, and we have different properties for different shapes. So if we have eccentricity that is going to be greater than 1, we're going to have a certain shape, and if we have eccentricity equal to 1, we have a different shape, and so we'll get those in a second. For a parabola, it becomes our same definition that we started with before, where that ratio is equal to 1. We can look at some GeoGebra examples and get a dynamic sense of how these work, but in general, we have these values that we can, if I have something bigger than 1, it's hyperbola, between 0 and 1, it's ellipse, equals 0, it's a circle, if it's equal to 1, it's a parabola. And we can use those definitions to expand what we had before. So this is what we had from before, A, B, and C. This is going to be a new value, this length d, which is our directrix radius. Same thing with hyperbola, but now we have this directrix radius. And we can get this, using these radii, we can calculate the eccentricity two ways. So we're going to use both of these formulas moving forward. We'll talk a little bit about where they come from kind of quickly, but in the end case, we're going to use these ratios to allow us to graph our values. So if we take a step back and try to figure out where these come from, we'll look at the focal points for ellipses and hyperbolas. I start with two focal points, and basically I have some constant value. Imagine this is the length of string, and we can wrap it around different pieces. So if we were to map that out, we'd get our elliptical shape, where this equals a constant, which is actually going to be 2 times a, because it's going to go all the way across, so our ellipse would continue across, and that's going to be our major axis, which is 2a. And we also have the ability to look at it for a hyperbola, where in this case we take a constant difference, and that difference is going to map out a hyperbola. And you see we can get bigger and bigger values for d2 and d3, just keeping that that difference the same. And we're again going to have our values. So if we look at where these ratios are coming from, let's look back at our elliptical example. That's b. That value is c to the foci, and that's 2a, because anywhere on my shape, that string is going to pull across and is going to become twice my major axis. And then I have a directrix on this side. I have one on the other side as well, but we only have to look at, in this case, the one over here for our example. And then we start to kind of pick apart different pieces. So I have the directrix is outside of my hyperbola, so D1 is larger than my A value. A is from here, the center, to the side. And then we can talk about some value, some number E, so that D times E will make them equal to A equal to each other. And we can think about E is going to have to be a value that's less than 1, as D is already greater than A. And so from there we can start to get our value for our eccentricity, and we just solve for it in terms of E is A over D. And that's one of our equations that we'll use. We can get a little bit more complicated here and start to break apart our pieces and get some more ratios. So we have that ratio there, and we have our ratio here, where we can start to set up an inequality. And that inequality is really these values from before, where we had a D2 value and a D1 value that we looked at before. And so we can make some substitution using the same principle as before. We can get some number E that will make those equal to each other. And again, we're looking at those ratios at the top. And we do some substitution and some elimination. So we put in this value for A, we make that substitution there, and we get, by canceling our pieces, that C is E over A. Finally, we apply our Pythagorean theorem to our pieces and be a little bit careful. We still have A, B, and C, but A is a hypotenuse, so A squared is B squared plus C squared. And this is going to be our equations for our ellipse, this ratio here. These are our values for eccentricity for our shapes as well. So this works for both of them. This is what we just talked about. We want to be a little bit careful with the A squared, B squared, C squared part. That'll be different for an ellipse and a hyperbola, but we can use the ratios constantly with them. And it's the same argument for the hyperbola. Won't go through the details totally, but we can see that this one is what you think of for your Pythagorean theorem, just the way the geometry works out, where C squared is A squared plus B squared. And so we can talk about how we use that to actually get our sketches. So I have, in this case, an ellipse, and I have my A and my B value. Again, A is always larger for the ellipse, and I want to get a sketch. And so I can get my C value using C squared is A squared minus B squared, and I get root 33. So I start to think about what my sketch looks like. So I have my major and minor axis. I can get my eccentricity, and from there I can start to find D, which is going to be the distance to my directrices. So D is around 8.5, and that's along the, it's perpendicular to the major axis, my A value. So if A goes like this, then my directrices go like that. And then I can start to just plug through it. So I have my values. I have my eccentricity, and from there we can start to solve for our pieces. So if if x is 3, we can solve for y, and then we can show that distance is going to be the same to the corresponding directrix as well. All that means is that we can use the properties that we looked at before to go from there. Alright, so all that says is that point and those points, if I take my distance and look at it, I'm going to get the same value that we did before using the eccentricity for our pieces, which is close enough just due to some rounding error based on our square root. All right. For our next one, we have an eccentricity and focal points. Again, we want to sketch a graph, and then second is find the parametric equations. So to do that, we're going to put our focal points on there. That's 10. And then there's my center right in the middle of that, and that's going to help me with my piece. E is greater than 1, so this is going to be a hyperbola, and I know that x is first because the foci align along the x direction. So I get x minus 1 squared, y minus 2 squared, that's just my center point, and then I'm going to put my values for a and b, and we use eccentricity to help me find that. There's my c value, and I know that e is c over a. I just make a substitution, and I get a is 4. And then I also have an equation that c squared is a squared plus b squared, which allows me to figure out b. B is 3, and now I have my equation of my hyperbola. If I want the parametric equations, we use our unbounded trig ratios, so it's going to be our secant and tangent functions, and we just have a and b attached to secant and tangent, and h and k are the locations of the center. We make our substitutions, and we have our parametric equations with the same information that we were given at the top.